And with that, I'll hand it over. I guess Otto, do you want to maybe give an introduction and hand it over?
Yeah, absolutely. Just quick introduction, guys. Thank you. Today we want to have an overview of the upcoming Polygon DID method. And for that, I brought the lead technical person in the team that has been in charge of all of that. So yes, pleasure to introduce Alexander, also known as Sasha. And he'll take it over. I'll just be here in the background. I can't hear you.
Might need to go into your Discord settings and select the input device.
Still no. Yeah, no, not yet. Try again.
1-1.
Yes,
Yep,
thank you.
all good.
Awesome.
Phew. Finally. Okay. So yeah, I will try to share my screen now, and hopefully you will see it. Okay.
It was there for a second, and then I think it got
Yeah.
dropped.
I can share if you. Okay, there we go. There we go.
Yeah, I believe I'm watching your screen now, sort of like an Inception style Discord for now.
do, do you see the presentation now?
No, I just see your Discord window.
Yeah, Otto, please, then can you share?
Yes, I'll do it.
Mhm.
That looks
Okay.
good. Yep.
Yep, finally. So yeah, I will present our solution. It's a set of tools and the protocol to solve some of the identity issues that we've seen. So we decided to design it from scratch and do a lot of interesting things using zero knowledge. So Polygon ID is a decentralized self-sovereign and private identity solution. We store some data on chain for the identities, but not claims themselves. We use zero knowledge to prove some statements about users, about identities, using credentials that we issued to them in a private manner without revealing actual data that is in these credentials. It's scalable in a way that credentials themselves could be issued off-chain, and then it's possible to use them on-chain and off-chain both. And we are doing this based on verifiable credential standards and DID method. So here you can see a regular triangle of trust where we have identity holder like a regular user, and we have issuer that could be like university or bank or government, and verifier that is in our case could be a smart contract that would be accepting some credentials from the user, or it could be a regular application, Web2 application that needs some data from the user. And what we have is issuer creates a credential, signs it, and sends to the user. And the user then can, using zero knowledge proof, can prove some statements to the verifier. For that, we have created, as we call it, ZK query language. So verifier can ask some questions like, please prove me that you have a credential, let's say you have a degree issued by some issuer, for example, university, some university, and that your average mark is some value higher than something. Or it could be, for example, would be a passport credential that has your date of birth, and then verifier may ask if you are over 18, for example. And user will have this having this credential can generate zero knowledge proof that he's over 18 or he has a diploma and so on. And for this to work, we have state lookups. So issuer is updating his state from time to time on chain. This is needed for the revocations to work, and also we have different types of credentials, like not types of credentials themselves, but kind of ways to issue credentials. But I will talk on it later. So, yeah, so that's an example with birthday, and user cannot just generate a proof of something that he has no credential of, that is not satisfying the request of the verifier. And it could be pretty complicated queries, but like multiple questions could be asked in same request. We have support right now for a few operations like equality, non-equal, greater than, less than some value, and also in set of values and not in this array. So for example, it's very useful if you want to check that person is not a resident of a country that is blacklisted, let's say. So we can, verifier can ask to prove that user is not from North Korea, not from some other restricted locations, just by supplying an array of country codes, and user will need to prove that country code in his credential is not in among them. Next. So we have a lot of different features that are coming from usage of Merkle trees. We're using sparse Merkle trees. So one of these feature is possibility to hide identifier of the user from the verifier and also from the issuer. So we are able to generate profiles. It's visually like just an identifier, regular DID. And for each interaction or for each counterparty, it could be a different one or can be reused. But it's possible to receive credential to one identifier and then present proof using different another identifier, but still inside circuit we're checking that all of them are belonging to this to that same identity, and we're checking it and providing a proof that user has this credential still, even if it was issued to another identifier that is right now presenting a proof. So that's a feature to hide identity of the user identifier and prevents tracking between different parties, including on-chain. So our identity is not linked to Ethereum keys, but rather to baby jab keys right now. And one identity can have many keys and can present proof from different Ethereum addresses, for example, for on-chain interaction. So we are solving this issue of tracking of users on-chain, but also off-chain. And to have this ability still to check that user key wasn't revoked, it's still valid. Without revealing his identifier, without revealing his identity, we need Merkle tree that we call global identity state tree, that is kept on chain in a smart contract state contract that we call it, and it has all the identities of that have transitioned their state. That's a technical thing, but we have initially identity is in genesis state, as we call it, when identifier is generated directly from the keys of this identity. And at this moment in time, identity doesn't need to be on chain to prove anything. So regular users, and it would be most of the users, will not need to have their identities tracked on chain until they do key rotation or something, or issue credentials. Yeah. And next slide. So as I said, identity itself can have many keys, and what we are doing is actually using another Merkle tree for that. So what's actually an identifier of the user? It's a hash of 3 Merkle trees. So each identity has 3 Merkle trees. One of them is claims tree, and it stores claims. And one type of the claim is authentication key that is used to prove something to other identities or to transact on chain, to change its state on chain. And we can store also other types of credentials in this tree, but it's not needed in most cases. but at least keys are in this tree. And even with credentials issued using this method by including into this tree doesn't have to be public, or it's actually private tree, and it's not revealed which keys are there and which credentials are there in this tree. The only thing that is published on chain is identity state. And there is two other trees. One of them is revocation tree. So when we are revoking some credential, we are adding its revocation nonce that is written in the credential. We are recording it into adding it into the revocation stream. Next slide. Yeah, and that allows us to prove different statements in a private manner. For example, this revocations tree and claims tree we are using to hide data that is used to generate zero knowledge proof. So there is no possibility for a verifier to know which credential was used, like it's not its signature, no its Merkle tree proof, nothing is shared with the verifier, only that it was issued by the correct issuer, by the some identifier of the issuer, and that inside the proof we are checking that it wasn't revoked, it was issued by correct keys that were not revoked of the issuer, and so on and so on. And some of the features that are coming is that we will also add Sybil resistant IDs. It's just because we are having these profiles, there is a need somehow still for some applications to be able to ask for a more static identifier for this specific use case. For example, if we are if a smart contract wants to make voting for something, then it would be good to have only one human, one vote, right? And then with this feature, it will be possible to for the user to prove that he has some specific claim, for example, that he is a verified unique human, and then without revealing this claim, without revealing identifier of the user, there will be another identifier generated for this application, for this, for example, specific vote, that this identity will not be able to vote again. So this is a basic features, and here's how our identifiers look like. So it's DID, then Polygon ID, then we have a network, and it could be Polygon, could be Ethereum. Then we have mainnets, testnets, and finally identifier of the identity that is it's actually hash of this Merkle trees, but also with some checksum and some flags at the beginning. Next slide. So here are what's on chain, and as this trees that we have. So only identity state of this identity is and only the ones that have, for example, rotated keys or something, they are going on chain through our state contract through calling a method called transit state. And the way it's working is that it's not linked to the Ethereum address. Rather, we're checking zero knowledge proof that it is still the same identity. It's correct one that is doing this transition of the state. And inside state transition circuit, we are checking that user have really control of this identity by checking key of that signed this generated this zero knowledge proof and so on. Yeah, and the rest that are in green, it's public data. For the issuers, they would publish claims tree root, revocations tree root, but also all the revocation tree would be published somewhere. We are not specifying where. We have right now implementation that we are doing it in two different ways. One is by asking directly issuer to give a Merkle tree proof that some specific revocation nonce is not included into the revocation tree. Another way is we have developed a so-called reverse hash service that you can ask the service to resolve some hash to its initial values that were hashed together to get this hash. And by using it's possible to just going from the top, from the identity state and to revocation tree root, and then knowing which path we need to take, we can resolve. Identity is able to resolve Merkle tree path and generate Merkle tree proof from it of non-inclusion of revocation nonce that of the credentials that is used right now. Yeah, and there also will be another way of doing it when revocation tree will be directly published on chain. Yeah, and revocation tree root is additional thing that when identity transitions its state and changes claims tree root, we can add it into this additional tree of claim roots. So when we are proving something, credentials, issuance of the credentials, we need to refer to some identity state of the issuer. And that can reveal sometimes a lot of information just because it could have been issued, for example, at let's say if issuer have issued in this state transition only one credential, then we would definitely know which one was used. So at least issuer would know which one was used. Of course, if they are like verifier and issuer has this if they collude and try to reveal who is talking with the verifier. Yeah, so it's an additional protection feature. So, but it's not used right now. Mitigated in with a bit different way. Could be mitigated. Next slide. So as I mentioned, there is two different ways of issuing credentials. Credential itself is a verifiable credential. It's a JSON-LD document, but we have different types of proofs inside this document. One of them is Merkle tree proof that credential was issued by adding this hash of this credential into the Merkle tree of the issuer's claim tree. This is useful when we want to prove, for example, that this kind of credential is unique one. Let's say if it's a competition, issuer would create only one claim that of a winner, right? So it will be possible for the user to prove that only he has this type of credential and no one else has it, for example. So it's more for uniqueness. For regular usage, we see that it will be more preferred to use another way. But also using Merkle tree type of issuances is also useful for on-chain issuance that we are developing right now. Just another way of issuing credentials also. So with on-chain issuance, definitely it's not possible to sign credentials with baby jab keys or any other keys. But it's possible to include credential into the Merkle tree and in this way issue it. It opens a lot of interesting use cases for on-chain issuance. Yeah, next slide. And second method of issuance is using just digital signature. So we're using EDDSA on baby jab curve for signing credentials. We are hashing contents of it and signing, and in most cases that's enough, and it allows to scale a lot because issuer doesn't need to update its state on chain. It just signs credentials using the key that is in its identity state that is published, and until issuer needs to revoke something, then it doesn't need to do anything on chain. But still, it's all the credentials issued in both ways are usable on chain, usable off chain, and it allows scaling. Yeah, but also baby jab type of credentials of signing is good when you don't want to have credential on chains, like even in hashed form. For example, it could be an issue for the issuer because under GDPR regulation, even hash of the hash could be considered personal identifiable information. So this is definitely a way for such data to be issued for such credentials. Next. Yeah, and that's kind of flow of the credentials. So issuers are issuing them, and for some of them, recording in some cases like revocation or issuing using a Merkle tree type of proofs, it goes on chain and updates its identity state. Then holder receives credentials off chain just by going to a website of the issuer and authenticating with the wallet, and receives these credentials in the wallet, and then user is able to generate zero knowledge proofs based on them and present to the verifier. Yeah, and actually one thing that I haven't mentioned is that using this technique, we are able to do also selective disclosure. So verifier may ask to disclose some attributes from the credential, and with zero knowledge proof, we are proving that some value of the some attribute of the credential has a specific value that user presents to the verifier. So it's still using zero knowledge proofs for selective disclosure, but we are not revealing anything else other than value of this attribute, not identifier of the user, not identifier of credentials, nor signature, nothing, no additional information is revealed. Yeah. So basically that's it. Yeah, if you have questions, would answer them.
Excellent presentation. Thank you for that. I think the question that is at least on my mind is how unitary is this whole system? Can parts of it be used with other DIDs, or can it be I don't know, like what's the thing that we could reuse for this DID work group, for example, from this?
Yeah, so right now we are looking into ways to simplify it and to decouple one thing from another. So definitely the key query language and then presenting of zero knowledge proofs based on credentials could be decoupled, and we are looking into ways to do it right now. Yeah.
Okay. So you mentioned a few methods of storing this data, like for the revocation tree. What about the so is all of it like stored through services that you provide, or is the user supposed to store some of it, their own data, or how is this supposed to work normally?
Yeah, so the revocation tree is stored on the issuer side, and when a user wants to generate zero knowledge proof, then he needs to go to the issuer or to some decentralized storage and fetch the data needed to generate this zero knowledge proof. So in this case, it would be Merkle tree proof of non-inclusion of revocation nonce.
I see. Okay. So there's sort of like a call home pattern here where the issuer is involved in like in the user's interaction with the credential. But you said that this only happens when the user wants to derive a new proof, right? Like, or does it happen also when the verifier needs to verify?
No, verifier is not communicating with the issuer directly. So verifier only receives identity state of the issuer that is on chain and could be checked on chain. That's it. So yeah, it's only users that needs to go and get this data. But also we, in some cases, for example, credentials could have short expiration, and verifier may say that, okay, I don't need to have any revocation checks, and so it's actually optional. Verifier may say that, yeah, I don't need revocation for that. But anyway, for the user's own keys, he needs to prove that they are not revoked. But obviously, he is controlling his own revocation tree. That's why he can generate this proof himself without a problem.
Okay. Is it possible that you can resolve one of these DIDs normally, like publicly, and get a DID document with keys and stuff like that, or is it always private?
So our DID method is kind of, while identity is in its genesis state, then it's not on chain, but still it's resolvable, but not to its keys. Keys are always hidden. Only issuers are revealing their baby jab keys. To other identities are not revealing, but in the DID document we have a verification method that is just it's directly using identifier of the user. So we just say that, yeah, like it would be with Ethereum address, right? So it would be not an Ethereum key, but a Ethereum address that you would need to prove that you are controlling. But yeah, it's just another way of proving.
I see.
Would it be possible to have this added to the universal resolver then? If these,
Yeah.
they can't be resolved, that would be great. So we can just start, playing around with different Polygon IDs and see what they actually look like.
Yeah. Actually, our guys are implementing it right now. So it's more or less finished, yeah, and we will contribute driver for universal resolver. Yeah.
Awesome. Thank you.
Yeah, first of all, thank you for presenting. Polygon was not on my radar at all, and all the stuff that you're doing, but it sounds very, very interesting. And I would love to go into more detail like later on when I'm just, researching and reading up on it. I feel like this short introduction didn't give me the full picture. But I have one question on the issuance method, method 1 with the claims Merkle tree. You mentioned that there might be some issues regarding GDPR and publishing hashes and hashes of hashes. Has your team had some contact with some legal people who had like an actual look into this? Because it has always been a blind spot for me of how GDPR would handle hashes of, for example, credentials on the chain. So it would be great to know if you know more about this.
Yeah, it's actually coming from legal guys. Yeah, but it's not written directly in the regulation that hash of the hashes is still PII, but if there is a way to prove that it's derived from the actual private information, then it could be thought as a still some personal information. That's why, yeah.
Okay.
Yeah.
So
For
it's
this,
still a blind spot.
yeah, it's
in a way.
in a way, yeah.
Thank you so much for the presentation. One quick question I had. So can you speak more on the key rotation management side of things? I was curious how you guys went about tackling the problem.
Yeah, sure. So keys are just regular claims in our games. In our case, we have initially we have just one claim that has a public key of the user, and it's kind of stating like this identity is controlled by this key. And then when we are presenting proofs, when we are generating proofs, we are using this key together with proving that it's not revoked, it's actual one. And we can add as many of such claims to the identity as we want. And later we can revoke keys that we don't need anymore. And in this way, we have this key rotation. And but identities identifier stays the same. It is the one that was derived from the genesis state of the tree of claims tree. And yeah, but we're just updating identity states on chain for this to keep track. Yeah, to then later be able to prove that some of them are rotated or not.
Thank you.
Are you already using this on Ethereum mainnet or just on Polygon?
Yeah, we had this on Goerli in tests and on Polygon, on mainnet and Mumbai testnet. We haven't deployed it on mainnet Ethereum because it's very expensive to verify zero knowledge proofs there. but still, it's possible. Yeah.
Yeah, hey, thanks for the presentation. I equally need to have more time to really digest everything. But what might help me doing that, in the beginning when you reference to the trust diamond, right? Of course, BBS plus signatures and zero knowledge proofs in verifiable credentials are, available there as well. And so it would be, I think, very helpful to compare and contrast with this more off-chain kind of focused world around zero knowledge proofs and SSI, and then compare it to what you're proposing or implementing. Obviously, with a much bigger focus on-chain type of interactions. But just compare and contrast. It doesn't have to be scientific, right? But just to give a notion to kind of reference with existing pictures.
Yeah. So BBS Plus, if I'm not mistaken, it still doesn't support proofs of data that is inside Credential, only selective disclosure. I remember there was in their documentation some words saying that it could be possible to implement in the future. But we have it implemented. We have this possibility to prove that like your age is over some value, or like as I said, that your country of residence is not in a blacklist, and also do selective disclosure. So in this way, it has more features. And also BBS Plus does not have a way to check revocation without revealing some identifier of the credential. So, for example, if you need revocations, then you would need to reveal some identifier of the credential and check it using revocation lists or some others like directly calling issuer status URL for this for some identifier. So it would reveal identifier of the credential used. So in this way, we have better privacy for the user.
Can you speak on the scalability of this design, I guess? Like, how does it scale? Like, can we talk like million credentials, thousands? Because working on the non-cred specification, trying to do something similar, there's like big issues with like revocation industry, like accumulators, like they're trying to do like all that, trying to get that figured out so we can scale more up than like thousands and whatnot. So yeah, I was wondering if you guys had like any thoughts on that.
Yeah, so it's only a matter of depth of the Merkle tree that you can increase number of levels of Merkle tree, and it will allow having a lot of like, for example, with 32 levels that currently we have for the revocation tree. It's like 2 trillions of possible nodes in the tree. It will be a bit earlier when collisions would happen, so it's not 2 trillions that are really usable, but yeah.
And then I guess in terms of like on-chain transactions, so I know like one thing that we're trying to do is like minimize the numbers of calls and things that we have to do to like retrieve calls that are like happening on chain. Yeah, can you like speak on that? Yeah.
For the verification or which calls?
Yeah, for like both the verification and like the issuance side of things. Like you said that like you don't really have to do anything related to the issuance until like you need to create like your revocation entry or something along those lines. So I assume that like issuing credential is relatively trivial, but yeah, mainly I guess like for revocation, it's like the most expensive part of the computation.
Yeah. So actually, yeah, using just digital signature with Baby Jab key, we can issue credentials in unlimited amounts without going on chain. Actually, identity even could be in its genesis state. I mean, issuer, and be completely off chain, but still be verifiable on chain. Yeah, but for the revocations to work, then first time any revocations will be done, this identity needs to go on chain to update its identity state, and it doesn't have to be one revocation done and one update on chain. So it could be batched. It could be millions of revocations actually in one update. So it's just you need just one update with a Merkle tree root, and what's inside it could be
whatever.
Yeah, completely like you can revoke everything in one shot.
Okay.
I have one more. So you mentioned that it's possible to derive proofs for parts of the credential or for predicates. Is it also possible to combine items from multiple credentials into one proof, like a sort of accumulator?
We are doing kind of this thing with off-chain. So we are actually we have a container that we call JWZ. It's modified JWT kinda. So, but instead of regular signature, we're proving that what's inside is coming from some specific identity using zero knowledge proof that it's coming from this identity, and inside of it there could be multiple responses to the queries. So it could be prove me that you have a diploma and you have a passport credential saying that you are from specific country and that you are of and so on. So it could be different actual zero knowledge proofs for each of these questions, but they will be under like in one container signed by one identity.
Got it. I think I was referring more to the situation about, like, let's say all of us wanted to interact with a smart contract, and for regulatory reasons, like I would only be allowed to interact with the contract if everyone that's participating is also like KYC checked or something like that. So the contract would hold sort of like a proof that I can verify publicly that everyone that has ever interacted with this contract has been KYC checked. And I was wondering if it's possible to kind of like combine proofs from these credentials that are coming from like different issuers potentially to different subjects. And yeah.
So we have actually implemented a few examples of smart contracts for verification, and one example is airdrop gated with credentials, so that you would need to generate zero knowledge proof that you have some credential issued by some issuer. So actually smart contract sets verification criteria for the user, and then user needs to submit zero knowledge proof that he is satisfying these requirements. And in this way it's possible to have one or many of such requirements, kind of requests to the user that user needs to prove before he can do some action in smart contract. And it doesn't have to be like one issuer. You can set a list of issuers that you are accepting credentials from. So for, let's say, it could be a KYC kind of credential, and you are, as a verifier, smart contract, you are trusting multiple issuers, and you would just provide their identifiers in a list, and that you're accepting credentials from these issuers.
Got it. Thanks.
I know we're at time, but maybe just a quick question on the proof system that you're using. I think it's IDEN 3, right? I forgot, is it still requiring a trusted setup, or is it getting into the Stark area yet?
Yeah, so we are using Gross 16 protocol, and it requires trusted setup.
Does it need it per circuit, or is it global or per circuit?
It's per circuit, yeah.
Okay.
It's per circuit. Yeah, it's also possible to use Plonk that has universal setup. We haven't implemented it yet, but I think in the near future we may implement it. Yeah.
Or
And
Stark, right? Or Stark that doesn't need a setup at all, right?
yeah, Starks doesn't need a trusted setup, but problem with Starks is that they are not verifiable currently on chain. At least
Ah,
it's
yeah.
too expensive to verify
Yeah.
Starks on chain. Yeah,
Okay. Yeah.
that's one of the constraints, but definitely it will be possible to use Starks off chain for off chain verifications, and we are looking into it also. Yeah.
Great. Thanks.
Awesome. Very cool. Yeah, so we are out of time here at this meeting. This was a great presentation. Like I said, I've been recording this. I will try to get it posted to YouTube this afternoon and share that out widely. And yeah, hopefully see everyone next week.
Thanks.
Yeah, thanks again.
Thanks so much for the time, guys. Really appreciate it.
Yeah. No, thank you. It's great. Thanks.